Well, student, we completed one topic. It is about the electric flux. So, in the next topic, it is about the Gauss law. That is your topic number 1.14. It is about the Gauss law. So, this topic can be explained by completing your concept about the electric flux. Because the equation of the Gauss law can be derived with the help of the equation of the electric flux. So that today we are taking the after electric flux, we are taking the word Gauss law. So derivation of the Gauss law is very easy. It is very easy. First of all, this Gauss law or this theorem gives the relation between total flux passing through any closed surface. It gives the relation between total flux passing through any closed surface and the net charge enclosed within the surface. This theorem gives the relation between the net flux passing through any closed surface and the net charge enclosed within the surface, or also you can say that the net charge enclosed by the surface. Okay? Now, to explain this theory, we are taking the one point charge Q. We are taking a one point charge Q. Around this point charge Q, you imagine one sphere of radius r. Around this point charge Q, imagine one sphere. There is imaginary sphere of radius r. And now calculate the flux link due to this point charge Q with the surface of the sphere. Now calculate the flux link with this surface of the sphere. Okay. So now the first statement, there is a S1 figure. There is a S1 figure. There is a point charge Q. There is a point charge Q. Imagine one smaller sphere. In this sphere, it is to be divided into a small element of delta S. This whole sphere, it is to be divided into a small element of delta S. So this is our delta S. This is our point charge Q. From the point charge Q, electric field is coming radially outward direction because it is positive charge. Because it is which charge? Positive charge. We know very well, student, if charge is positive, electric field is radially outwards. If the charge is negative, electric field is radially inwards. Right now here is a positive charge. From this positive charge, the electric field is radially outward direction. See, this is our area element. Now, area vector of this element, can be found out by placing the pointer normal to the plane. So that student, now place the pointer normal to the plane. So now in this theory, vector E and this area vector both are in which direction? Same direction. Both are in which direction? Same direction. So that through the equation of the flux, delta phi is equal to vector E dot delta S dot vector delta S. Now what we require? Electric field due to point charge. Student, electric field due to point charge can be given by 1 upon 4 pi epsilon 0 q by r square into r cap. Electric field due to point charge can be given by 1 upon 4 pi epsilon 0 q upon r square into r cap. N vector delta S replaced by delta S into r cap. Why we are multiplying r cap? Because this area vector lying in the direction of the radius of the sphere. So that we are multiplying what r cap. R cap is the unit vector in the direction of delta S. So that we are multiplying what r cap. The simple delta S replaced by the delta S into r cap. Now r cap dot r cap, it is equal to 1. R cap dot r cap, it is equal to 1. So to relate the above equation, delta phi is equal to 1 upon 4 pi epsilon 0 q by r square into delta S. So this is the equation of electric flux linked with this only one area element. To calculate the total flux, through the sphere is obtained by adding up flux through all the different area element. A simple thing, student. Now to calculate the total flux linked with this sphere, please adding up the electric flux due to the all area element. This is our first area element. We can draw the next area element. We can draw the another area element, third one. we can draw the fourth one area element, then calculate the flux linked with the each area element, then adding up, then make their addition, then finally we can calculate the total flux linked with our sphere. Okay, so that the next step, student, the total flux through the sphere is obtained by adding up the flux through the all different area element. So the student, flux phi is equal to sigma all delta s. So rewrite the same equation, q upon 4 pi r epsilon 0 r square into delta s. Okay, so now the next step, student, sigma all delta s q upon 4 pi epsilon 0 r square into delta x. The each area element of the sphere is at the same distance r from the charge. So on first element, distance from the charge it is what r. Suppose we draw the another element whose distance is also what r. We draw the another element whose distance is also what r. We draw the another element whose distance is also what r. All the area element it is to be lying at the same distance from the charge q. So the student, this value of the r remains constant. This whole term remains constant. That is to be write down outside of this sigma. Write down outside q upon 4 pi epsilon 0 r square sigma all delta s into delta s. So this equation represents our total surface area of the sphere. So that this is replaced by now only s. This is replaced by now only s. Therefore q upon 4 pi epsilon 0 r square into it is s. Where s is equal to 4 pi r square, total area of sphere. Area of the sphere is equal to what? 4 pi r square. So now s replaced by it is a 4 pi r square. So now student, 4 pi it is cancelled. Then r square also what cancel. 4 pi cancel, r square cancel. Which term remaining now? Phi is equal to q by epsilon 0. Phi is equal to q by epsilon 0. It is a equation of Gauss law. It is a equation of Gauss law. Where q is equal to sum of the electric charge enclosed by the Gaussian surface. Sum of the electric charge enclosed by the Gaussian surface. So around the point charge q, we imagine a sphere. That sphere it is known as the Gaussian surface. Imagine of a sphere, it is known as the Gaussian surface. Shape of the Gaussian surface it is arbitrary. This electric flux linked with any Gaussian surface does not depend on the size and the shape of the surface. Electric flux linked with any surface, closed surface, does not depend upon the shape and the size of the surface. You can imagine any type of closed surface that is known as a Gaussian surface. Okay. So now this above equation represents the Gauss law. So now please given the statement about the Gauss law. There is a statement of the Gauss law. It is to be given like this: the total electric flux linked with any closed surface. Total electric flux linked with any closed surface is equal to the ratio of electric charge enclosed by the surface to the epsilon 0. It is a ratio of the electric charge enclosed by the surface to the epsilon 0. Once again, student, the total electric flux linked with any closed surface is the ratio of electric charge enclosed by the surface to the epsilon 0. Like from this equation we can give this statement. It is simple things, ratio of the electric charge to the epsilon 0. Okay? So now this Gauss law, which can be used to find out the electric flux enclosed by the to find out the electric flux, or it is to be used when the charge is enclosed by the any Gaussian surface, that can be calculated by using the word Gauss theorem. Student, related to the Gauss theorem or electric flux, there are some examples are given. First example, cylinder placed in a uniform electric field. Cylinder is placed in a uniform electric field. So this is our cylinder. It is placed in a uniform electric field. Calculate the flux linked with the surface. Student, these are the sides of the cylinder. And this is the curved part of the cylinder. With the curved part, electric field lines are parallel. So the flux from the curved part it is 0. Flux from the curved part of the cylinder, it is 0. But we can calculate the flux linked with this first side of the cylinder or on the second side of the cylinder. Student, for this side, area vector is normal to the plane towards the left side. For this side, area vector towards the right hand side. What happened? For the first surface, vector S, vector E opposite to each other. Angle between these two 180 degree. For the second surface, vector S, vector E both are in the same direction. Angle between them is what 0. Like here for the first surface, angle theta is equal to 180 degree. For the second surface, the angle theta is equal to what 0. So the total flux linked with the first and second surface, phi is equal to phi 1 plus phi 2. Where phi 1 is equal to Es cos 180 and second one it is a Es cos 0 degree. Cos 180 minus 1, so it minus Es. Cos 0 1 plus Es. Minus Es plus Es is equal to 0. Total flux linked with this cylinder it is 0. Why the answer is 0? Why the answer is coming 0? Because the number of field lines are entered through the first plane, the same number of field lines leaving through the second plane. Number of field lines entered through the first end, the same number of field lines are leaving the plane. Therefore, the total flux linked with these two surfaces it is 0. So another examples. So this is our any closed Gaussian surface. Closed Gaussian surface. How many charge enclosed by it? Total 3 charges enclosed by it. This Q means what? Sum of the electric charges enclosed by the Gaussian surface. Total number of the charges. How much number of the charges are enclosed by it? Total 3 charges. So that simple equation. Flux phi is 3q by epsilon 0. So another example. Again this is our Gaussian surface. Plus q charge minus q charge. Or also we can say that dipole is enclosed. We know very well. On the dipole total charge is 0. Therefore flux is 0. So next example. See this is our cube. Charge q is placed at the center of the cube. Through this charge cube, all the field lines are linked with this cube. The total 4 answer is possible. 4 answer is possible. Total flux linked with the cube, that is phi total is equal to q by epsilon 0. Total flux linked with the cube, that is phi total is equal to q by epsilon 0. But student, they may ask, calculate the flux linked with the any one of the surface. Student, total number of faces in a cube are 6. See, this is the answer of the how many faces? Total 6 faces. 6 face flux is q by epsilon 0. So due to one face or due to one surface, flux is this. Answer is q by 6 epsilon 0. Once again, student, due to 6 face, flux is q by epsilon 0. So due to one face, flux is this. Answer will be what? Q upon 6 epsilon 0. Therefore, flux linked with the one of the surface is equal to q by 6 epsilon 0. Student, in a cube, total number of corners are 8. Due to 8 corner, flux is q by epsilon 0. Due to 8 corner, q by epsilon 0. So due to 1 corner, flux is this. So q by 8 epsilon 0. The flux linked with the one of the corner of the cube, that is q by 8 epsilon 0. And these are the edge of the cube. These are the edge of the cube. Total number of the edge in a cube are 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For a 12 edge, flux is q by epsilon 0. For a 1 edge it is this. So that answer will be flux edge is equal to q by 12 epsilon 0. That answer will be flux phi edge is equal to q by 12 epsilon 0. Okay, next example. If charge q is placed at the center of any face, now the charge q is placed at the center of the one of the face. Student, to calculate flux linked with this cube, first of all, using the another cube that is enclosed this charge. So we draw the another cube that is enclosed the charge. Now the flux linked with the one of the cube. So due to 2 cube, flux is q by epsilon 0. So due to 1 cube is this. Answer will be q upon 2 epsilon 0. Therefore 5 cube is equal to 1 upon 2 epsilon 0. Okay. So next example. Charge q is placed at any vertex of the cube. It is to be placed at the corner of the cube. Student, to enclose this charge, total how many cubes we require? Another 7 cubes we require. 1, 2, 3, 4, 5, 6, 7. By using the 7 cubes, this charge is closed. So the student, now the flux linked with the one of the cube can be given by, that is 5 cube is equal to q upon 8 epsilon 0. Because this is the answer of the how many cubes? It is the answer of the 8 cubes. Answer of 8 cubes. So due to 1 cube is dash, that is q upon 8 epsilon 0. The total flux is q by epsilon 0, but due to 1 cube it is what 8 q upon 8 epsilon 0. So the student, these are the examples are related to the word Gauss law. Student, two equations are completed. First equation, relative flux phi is equal to vector E dot vector delta S in a uniform electric field. Another equation, in a non-uniform electric field, flux phi is equal to integration vector E dot vector Es. And we studied the word Gauss law, that is the flux phi is equal to, it is a q by epsilon 0. Now the last topic is remaining in this chapter, that is your application of the word Gauss law. Okay?